Thank you very much, Mike. Hi, everyone, and welcome to the session. It's a great pleasure to speak at this conference, and this is an opportunity for me to update some of the experiences we've had with transformers, which we've been using now for a couple of years with great success. So just to start off briefly, to talk a little bit about who Autodesk are. So we're a 40-year-old software company that is based in the San Francisco Bay Area as our HQ. You may have heard of some of our most well-known products include things like Revit, AutoCAD, Fusion 360, Maya. So across the whole domain of professional design and indeed some hobbyist design, development, manufacturing, and media and entertainment, our software is the support that provides the bridge between the idea in the creative's head and the realization of that thing, be it virtual, digital, or physical. And very often you'll find that any number of projects that produce something often involve our software. That creates a very interesting situation from our team's perspective. So the team I'm on are focused on the e-commerce and on the customer empowerment side, which is to say that we look at how we can assist users in solving problems that they may have to resolve issues with using the software, or to which matters an awful lot because many of our users have spent much of their careers with our software and they know it extremely well. So when they have a problem that they need to get solved, it's pressing because it is their job, and it could be a major project that's on the line. And so it's important for us to be able to deploy the best possible software and the most advanced techniques to help get those solutions to their resolution as quickly as possible. Similarly, when it comes to making it easier for customers to execute transactions as they grow their company or expand their expertise, we're being able to make better use of the whole digital infrastructural life cycle of our product ecosystem is a part of that range. And so today I want to talk about that, which is the experience that we've had using transformers as a way of facilitating the improvement in the experience for our customers all around our domain. So I feel a little bit like this is probably a slide that when I first talked about transformers, I had to introduce them in a very concrete way. I think most people would not have heard of them and would not know what I was talking about when I spoke of them. But nowadays, I think it's very apparent that transformers are kind of a central part of the way people think about not just text machine learning, but a wide variety of other applications. In essence, you can think about transformers as being applicable across a wide variety of tasks, text classification being one of the most common ones. Language generation is probably the highlight in terms of the most eye-catching one. And then translation is also an area where transformers have had extremely high value. And in all of those things, you can see the same kind of components too, which is that transformers provide increased flexibility. They allow for a much wider array of success, and they allow the models to take better account of what's going on in the language in a way that is more subtle than previous techniques have allowed for. They are, in fact, as you think about it, pretty much state of the art in almost all NLP applications at this point. They, the underlying technology allows a wide variety of different approaches to training and to, greater flexibility in the type of data that you may have and the type of facility that you have. So how does very broadly a transformer work? What's different about it? Well, a transformer kind of thinks about language in a different way to previous models, which were largely sequential or bag of words in their thoughts. So either you looked at individual tokens one at a time, or you looked at a sequence of characters or words in the order in which they appeared in the sentence. And if you think about it, humans don't probably do that. It seems like intuitively, at least, or when I think about how I understand language, I kind of encode the sentence. So I listen to the sentence in a runline way, but when I get to the end of it, I listen to the whole thing again and replay it. You can think about all of the ways that puns work as being evidence that really you look forward and backward across all the different tokens before you come to a conclusion about the meaning of the sentence. And compositionality is that sense that, the meaning of the words beside each other all define the overall context and sentence and context and meaning in the sentence. And transformers attempt to do something similar by looking at the position, the relative or absolute position of the token, along with the neighborhood of the token when it comes to a particular meaning. And so the other key thing about transformers that's important is that we don't come at this from scratch. So, transfer learning, which has transformed, is equally important in the change in the way we think about machine learning in general, and coming from our colleagues in the vision domain has also transformed the way we think about how we build these models. So instead of starting from scratch, one of the big challenges with these transformers is to get them to learn enough to do something effective. They need a large amount of data, and so thankfully, this has come about in parallel, this idea that instead of trying to just train everything from scratch and build your model from the ground up, what you will do is someone will train a large language model on a general set of objectives on this multitask learning, and that can be token guessing, it can be a wide variety of different objectives depending on what you're kind of building, and then we transfer. So we either take that model overall, or we kind of fine-tune that model. We kind of make the model more expert on a specific area, a domain specific area, before we use it. So essentially the three key takeaways from transformers are: one, we look at multiple words at the same time, or windows of words together. Two, we only use effectively that attention model as a way to structure the model, so we don't have our current structure and we don't have convolutions in there. And three, we take advantage of the fact that we have trained a large model and then repurposed it rather than trying to build it out in one go. So the dominant kind of technological feature of the current world of transformers as well is the use of the Hugging Face library and the Hugging Face team. And I believe Hugging Face, the CEO, was speaking not long ago at this conference, so I will hopefully not overlap too much on what he said, or certainly not disagree with it. But the key point about this is that in transformers, we've seen an unprecedented degree of sharing by large and small organizations in their ability to concretely make models, code, and architectures available for people's use throughout the community. And so this has been one of the most wonderful experiences. It's been the open source and open nature of the engagement, the ability for us to get from a research paper to a model to implement it in a business process has been extraordinarily fast, and the amount of learning and value that's been going on has been incredible. And so it's fair to say that transformers are eating the world, much as software ate the world before, and I think we will continue to see a value in the growth of these kinds of technologies as time goes on, and we're only seeing them scale up, and we're only seeing more creative and more fascinating uses for them and more techniques for making them available to everyone as we go forward. And I think from my perspective, this is a very exciting time because the technology has matured and has begun to take on another layer now, a second leg, where we're beginning to see it. And so we've been deploying transformers for nearly 3 years now, and we would like, we have some background on what we want to do. So in my specific domain, what would I like to be able to talk to you about today? There are, as I said, lots of different ways to use transformers, and ever growing every day. And I think one of the ones that I want to highlight is the one that I think is often emphasized in the kind of academic research area for very good reasons, and also is probably one of the less exciting ones from the perspective of what you might do to get a lot of exciting social media likes. This is not about generating this is not about generating new text. This is not about kind of image to multimodal kind of work. What we're really talking about here is a key thing that is very important to a lot of businesses and very industrially relevant, which is I have some business process that I'm trying to automate or to accelerate. And this can be in our own examples. We've had great success with, for example, the question about how to route specific domain-specific questions about products to the correct support team. And that sounds like a kind of a flat or slightly boring, or maybe even in some minds solved problem, but you'd be surprised at the variety with which customers will phrase their problem and a number of ways in which you can have to deal with the overlapping and noisy data that you get from a real business process. So it's important to think about the fact that while this isn't the most futuristic or science fiction-y kind of application area, I think it's one that demonstrates the real value of machine learning, especially with transformers, and demonstrates the sort of practical experience that you get along the way. And my goal with this talk is to talk to you about all the ways you can use transformers to solve parts of these problems, and hopefully along the way also illuminate you with some of the techniques and methods that we used. when you talk about these sorts of things, in an ideal world, you would just say, oh, well, look, we'll just get everyone to tag all the data and we'll go back and forward through the data and it'll be easy. Or we'll hire an external tagging company to do these things. Very often with these kinds of business processes, there are two challenges there. One is that the process is designed to be efficient, and so anything that involves additional work such as metadata tagging, such as adding work to it, often is costly and therefore will be noisy. Things move, methodologies shift, organizations change. And trying to do this with an external vendor can be difficult because very often these are not intrinsic kind of differences. Like the reason you go to team A versus team B is different in one company to another and doesn't necessarily entirely depend on a logical kind of externally valid hierarchy of conceptual differences. And so there's this arbitrary nature to the way we're grouping these things that is very flexibly accommodated by a neural network, which can kind of expand the manifold around multiple distinctive clusters, but which does nonetheless have this challenge that you need to generate the data for. And lastly, user text is always difficult because people type with a lot of typos, they type with all sorts of descriptive challenges, and very often what you're trying to do is they don't have that kind of convenient thing of having the answer encoded in the question. Instead, they genuinely don't know how to solve their problem, and so we have to think about a little bit about how we're going to deal with that along the way as well. So there are three stages that I want to talk about today. The first is how to handle the data, looking at this thing about data cleaning, labeling, managing the noise, and so on. And then the second one is about training, which is some of our experience with training models and some of the interesting things that have come out of training and best practices that have come there. And finally, I'll talk about our experience with inference, where we had we've tried a few different approaches and a few different techniques, and some of the things that we've thought about along the way. And what I've tried to do is, in this talk, I have mostly tried to each give you an example or some code or some pointer that I can give you in the direction of a methodology or an approach or some path along the way. So if you yourself are faced with this challenge of developing a supervised learning environment, or indeed something similar but not quite the same, then hopefully in the process you'll be able to leverage some of these tools on the process. I should also say that while this is a particular example of these things, we don't necessarily as a company endorse any particular approach. These are just some of our experiences, and mostly this is my personal view and my view as part of the team. So data cleaning is why data scientists drink. I think that's the easiest point to think about along the way here is that, we talk about as a rule of thumb spending 4/5 of our time trying to disentangle what's already been marked up. We're trying to find out why a piece of data is in the format that it's in and trying to label out what's going on along the way. And it's fascinating to look at how you think about a business process, and you kind of see a very convenient and very nicely developed flow diagram or a kind of set of documentation that describes a bit of behavior, or even a process that seems very nice, very tightly wound. And when you look into the detail of it, there are a couple of things that go on in practice. One is, for example, that you can have the challenge that the misalignment of incentives is very strong. So in the customer support domain, one thing that you find very often is agents will go the extra mile to help their customers. And that can be great, but it also undermines your process, because now for some reason, one team is able to solve a problem unexpectedly vis-a-vis their ontology or their taxonomy. And the reason for that is that they don't want to transfer the customer, because why would you if you can solve it for them? And moreover, that's a better experience for everyone. So the challenges of kind of latently saying, oh, it's almost certainly the case that we will just track where things go and get all the data out of it, never really works along the way. So very often what you're presented with is a pile of data, some historical record of some of the behaviors that have gone on along the way. And you need to think about, okay, how do we extract from this the distinctive attributes and the clusters of distinctive behavior that we can use to then get us to something that we can train a machine learning model from, and begin to automate the decisions and begin to cover the three types of problem that you need to think about. The first one is the model has to be right when the happy path is engaged in. So when the customer goes to the right place and clicks the right thing, the model needs to also guess that. When the customer goes to the wrong thing, we need to correct their behavior. And thirdly, when there's a mystery, when there's some other exception to the system, we need to be able to understand what those are and prioritize whether or not we want to be able to do that, or be able to just simply pull things out along the way. So given that open pile of data and that open pile of stuff, what are some of the modern techniques that we can use to try and address this problem? And some of these I wish I'd had 3 years ago, because we did an awful lot of manual tagging and manual process engineering to do this. And these days, that's much more of a tool-assisted approach now. So the first one I want to talk about is probably one of the most exciting things that we've seen in the way that machine learning with large language models has moved forward. And this is the concept of zero-shot classification. And in a zero-shot domain, what we say very simply is, hey, you know, we have built this model. It's several hundred million to several billion parameters wide or large, however you want to describe it. It has a huge amount of encoded information in it, not just at a low level, not just at the simple level of you know, understanding the, I use the word understanding loosely here, but not just in the sense of having a sense of the proximate order of tokens, but actually those things emerge much more complex patterns that can be dealt with by the, can be used for the purposes of doing things. So before we even get into training the model on our own specific way, and before we do that sort of thing, why don't we just see what is already known, what is already present within the model, what it can infer along in the process. And so what I really like about this is, in this case, we're talking about the zero-shot classification using the default transformer model. And underlying this, the way that this kind of works is that it takes advantage of the fact that the models can score 2 sentences and decide whether or not they are similar enough or they entail with each other. So for example, I have my 3 sequences here. Are you looking for social media followers? I'd like to purchase 10 units of your product, and my product ordered on the June the 10th has not arrived yet. Can you help? And I supply 2 things to the model. I supply a set of sequences, and I supply the potential candidate labels that I'm interested in. And at the top, you can see here, we have this hypothesis. And what we do is we say to the model, we give it the sequence, we give it the hypothesis with one of the labels in it, and we ask the model how much do those, based on everything that the model has seen in all of the thousands and hundreds of thousands of documents that it's seen before, how likely is it that these encode with each other? And so you can see that, for example, what you would have here is you would say, are you looking for social media followers? And the model queries, it says, this is a sale, this is a order support, or this is a promotional message. And the model will then, without being prompted in any specific training way, give you back this score for these things. And I've taken these examples, and this is the Hugging Face code for this, largely from their website. I've simply changed the examples. And if you run this code, you will get back correct labels for this. In practice, when we use this, we find it to be a great way to start down the path of thinking about how we might detect clusters in the models. Excuse me, one of the challenges, or one of the biggest challenges here, is you've kind of got yourself, it's a bit like the kind of that old adage about, you know, when you start using regular expressions, now you have 2 problems. The same thing can happen with zero-shot learning, which is the choice of candidate labels is essential to how you begin to develop effective zero-shot labeling. And it's not at all obvious what types of labels and what types of and even if you want to change the hypothesis, what types of hypothesis will give you the best kind of behavior. And so in my example here, I wanted originally to look at spam and not spam as a kind of example, and I couldn't find a good combination of examples that work for that. So that's one challenge, is that choosing the candidate labels appropriately can be difficult and can lead to some unexpected behavior. The second challenge that you have here is that these things need to have been seen, and they need to be kind of intrinsic to what the model has seen in terms of categories. So it works extremely well where you're trying to do very broad kind of categorizations of the kind of brown corpus type. If I want to learn the difference between sports and news and technical data, I might be able to do that pretty easily, or science fiction. It's very difficult for it to learn about things that are very fine-tuned differences or very subtle differences in high context, because it just hasn't seen that stuff. It hasn't learned in that way to distinguish those tokens. So I think I'm very excited by how we've used zero-shot classification as a first step towards these things, but it's really just another signal and another piece of noisy data. And so my recommendation is try it out, but think about how you can use it laterally to the rest of the data that you have as a supplementary rather than a confounding value. And that leads to the second thing that I think is interesting in data preparation, which is the move towards using weak supervision. So in this case, we're going to accept the idea that labels are difficult to use. We're going to accept that we're never going to get a completely reliable set of data. And in fact, even if we do a lot of hand labeling by very committed expert users, we're still going to have some level of error in the model. And so what we can do is we can say, let's combine a whole different set of rules of thumb. If it mentions a particular token, if it has these keywords in it, if it's of this length, any number of rules that you can think of, along with the output from different models, previous information from the system as a way, and then attempt to learn some sort of a surface, some sort of a model that will then label that data for us. And the nice thing about this is this allows us to attack the problem of getting really high quality data-centric training of the models without having to be perfect. The other thing you can do at weak supervision that I think is very powerful is that you can cheat. So you can use post hoc knowledge. So for example, you can look at what happened at the end of something, use that data to train backwards and use it as a label as well. So because we can look at only, for example, cases that have closed, or only look at sales that have completed, and then use all of that data, but the input is only going to be the piece that you get at inference time as well. So it allows you to take out the post hoc knowledge and take advantage of it along the way, and take advantage of all of the active and interactive learning platforms that are out there. So one example of this is the Flying Squid platform from Hazy Research, who previously had built Snorkel. And I think that that's a very interesting thing to combine. And now you have this opportunity to build things where your data set is now something that's flowing, and you stop thinking about data sets as this diachronic slice that freezes in time and has spent a lot of money developing, and instead it becomes a flow of data that's continuously being added to. So training is the next step that we want to think about. When we come to training a model for supervision, what we think about is this idea that what we want to do is we want to address the fact that we want to take the model and make it very specific. At Autodesk, we have this all the time because we deal with a huge amount of technical data, and we use entity-focused, we often use entity-focused type data. So there's a lot of talking about specific functions, specific words in a very specific context. So the meaning of line, the meaning of wall, the meaning of those sorts of things can be very importantly different, whether you're talking in a manufacturing or an architectural context. So I'll refer to my colleague MC Hammer, who tweeted this a year ago now. The difference between one-shot learning and zero-shot learning, and in fact, all of the few-shot concepts is very interesting, because with these large language models, it is a kind of an interesting open question as to understand how much are you changing that base model when you add the fine-tuning on top of it, and how much is it dependent on the underlying model for it to be able to recognize things. And I think those are essential things to understand. There's only so much changing you can do as you can kind of build up the model, and as you kind of build up the training. So I think very importantly, when you're thinking about these sorts of things, there's a lot of hyper parameter tuning and stuff that can be thought of, but very much the first step that I think is often to be thought about is actually just to think about the base model in a very specific way, and think about what the base model might contain that might help you move forward. And so taking that into account, there are tens of thousands of models available on the Hugging Face repository, all of them available to be downloaded. And it may be that one or more of them is the first place that you might want to address trying to change how your model behaves. Before you get into the very complicated hyperparameter tuning, try a few different fundamental models or base models and see if any of those improve the behavior along the way, because they think about the relative position of the tokens better, or they behave in a different fashion. This is the simple example of the code, again, taken from AWS. This is how to train a model on SageMaker. And what I will say about this that's useful, the key thing in here is that there's this train.py file, and one of the key things in there is to understand what loss function you choose and what evaluation metric you choose, and those sorts of things, along with the ability to choose the correct baseline model, often have a much more productive effect than doing too much in the way of tuning. And actually, it's a nice relief that by and large, for the kind of fine tuning work that goes on, there isn't a lot to be done in terms of the kind of tuning that used to be done, or if you had to do stuff in SVMs or more shallow learning models. Very often what you find, though, is that people don't actually want to do direct transformer-based modeling. What they want to do is add the language of an input to a set of other things. And what you want there is you want a stable set of embeddings from which to work from. And one of the nice things there is to have a look at things like the sentence transformer approach. And what this does is this goes back to this idea of, hey, language is a feature. Maybe we concatenate that with some other operational attributes that we want to worry about and some other features that we want to think about. And from there, we're going to go, rather than going into the kind of trying to get the machine, trying to fine tune the ML model or fine tune the transformer model entirely to fulfill our needs. And I think that one of the things that we found along the way is being able to do this and to fine tune these. So one of the things you can do with these kinds of models is you can continue the training. So you can say, here's a bunch of further examples that will allow us to customize the vocabulary or customize the similarity function that the embedding space by means of sort of showing more domain-specific language on top of the existing one. And whether you do that with a classical single transformer, or in this case with these sentence transformers, which use typically use twin models and are contrastively learned, depends on what data you have available and how much time you want to spend. But I think very often it's very useful to be aware that you have this opportunity to use the encoding, use some sort of a substantive method to get a stable embedding, which is then just a feature to something else, to some other feed-forward network or XGBoost or whatever model you want to use on top of that, that would allow you to build a larger model. Because the context there is that these things allow you to do these things. In the past, there have been experiments to try and use custom tokens, to try and use other approaches to do that. And I think your mileage may vary, but certainly along the way, we found that stable embeddings are a very powerful way of addressing a lot of problems, and using things like a fast approximate nearest neighbor search along with an embedding can be a very powerful thing. One warning I will give you here is that for all of these things, we do find, and there's support in the literature for this finding, that where they're entity focused, where there's a lot of focus on the specific words rather than the surface meaning of the sentence, you can run into a lot of problems because model similarities is kind of aggregate over the whole sentence. And so trying to get a model to learn the difference between how do I install Revit and how do I install AutoCAD, being very different things compared to, because they're both installation questions, that kind of iconographic kind of question is very difficult to fine tune. And so something that you need to have a very strong understanding of the behavior of the model you expect before you do there. And that leads to my final point on training, which is the importance of being able to do discipline, to approach testing of the model in a disciplined manner. And I will draw your attention in this case to work by Microsoft Research on what they call the checklist process. They define 3 types of tests that they think should be done, and they use a transformer to help test these things. So this is why this ties back to this talk so nicely. And what happens is that the first one is the idea of a minimum functionality test, which is equivalent to a unit test in programming. These are some things that the model should just get right. So if it's a sentiment model and I say I am happy, it should always return a positive sentiment for that. An invariance test is then beginning to sort of think about the fact that these models can learn spurious correlations. And so it should be possible for us to understand whether or not the model is beginning to behave spuriously. So for example, taking my sentiment analysis example, it should not matter if I say it is Monday, I am happy, or it is Tuesday, I am happy. The model should be able to know that the day of the week is probably irrelevant to my statement about my sentiment, however I may feel in a cure way about whether I do or don't like Mondays. And finally, the directional expectation test, I am not happy versus I am happy, those sorts of things where you expect a change in behavior from the model, making sure all of those are happening. And these checklist approach, where it uses automatic augmentation to help you with it, and they have a whole interface for it, I think is a very powerful way of scaling up the training and allowing you to build and test more models, because you can automate the whole process, or at least programatize the whole model in an effective way. So finally, inference. And inference has been a kind of an exciting topic. I know that all of the major providers, including Hugging Face, are very intent on helping people to get their models into production. And this comes from the fact that 2 years ago, it was considered difficult, verging on impossible, to scalably deploy transformer models. They did and do require GPU or other custom hardware. Certainly the CPU inference of models is expensive and difficult, and so along the way there are other things to think about there. Two approaches that are kind of more common in the past. One was to use distillation, which is to say that we would train a simpler model from a larger one. That's still popular, but and in fact training on distilled base model has proven to be a very effective approach. And quantization, which has taken a large leap forward now that there are the kind of dynamic and mixed mode quantizations that are highly effective. And people are doing all sorts of fun things, getting down to 8-bit and below. And I think this is very exciting, but very intensive and very expensive. And so from my perspective, where I have a limited budget of time, I think I'm more interested in opportunities to scale things faster and more easily. So one example of that is in custom hardware. So we had an opportunity to work with the AWS SageMaker team on their Inferential custom inference chip. And the nice thing about this is that this is all the code you need to take a pre-trained model and make it a one to deploy. And I think anything that is like this, where there is a simple path from development to production, is something to be encouraged. And Inferential is one of these. There are several other examples out there, and all of them have the value associated with them, that what we can do is we can build a model, take it to production, and then speed it up and scale it out. And we saw 4.9-fold increase in throughput, which for us was highly valuable and highly powerful. So in conclusion, what I want to say is that I think the best metaphor for a transformer in my mind is this Swiss Army knife. It's a very powerful, very extensive tool, but it's not always the solution to the problem. The thing about it is that they do impose some constraints on you. They do require a large amount of resources to train and to build. The largest models right now that I've seen are in the 20 to 30 gigabyte size, which is just and requires 2 to 3 times that in terms of RAM, in terms of memory to load. So that's a sizable model to think about. And thinking about all of the tools that are available to you can be a bit overwhelming. So taking a disciplined approach to the understanding of it, making sure that you have a process that both involves a continuous data stream that continuously updates the value of things, and that you have a checklist type approach to ensure that your model is consistently behaving over different versions. And finally, looking at scalable inference and scaling up how you offer the service is a key point to controlling the costs along the way. And maybe it is the case that this could all be done with a naive base classifier, but most of the time, the power of the transformer is in the flexibility it provides and in the ability to get something out quickly that then can go to the next step. So thank you very much. I will happy to invite any questions that may arise, and hopefully I haven't run too far over time. Thank you to everyone.